Hello, my smart and talented friends, and welcome to the Global Science Network. Today we're going to be talking about digital logic gates, and I'm actually going to show you how to build an AND gate, NAND gate, OR gate, NOR gate, exclusive OR gate, and exclusive NOR gate. In addition to these circuits, I am going to show you how a transistor works as a switch, how to build an inverter. This circuit just shows that a switch and an inverter are opposites of each other. And this one is how to build a buffer. If you stick with me until the end of the video, I'm going to show you how to implement AND gates using integrated circuits. This is actually really easy to do, but a lot of people do it wrong, so this is something I wanted to show you. There's actually more than one way to implement each type of logic gate. For example, I'm going to show you 5 different ways to build an AND gate, 4 different ways to build an OR gate, and 4 different ways to build an exclusive OR gate. And it's important to understand how to build all the different types of logic gates so that you pick the best one whenever you're building more complex circuits. For example, in our next videos, we'll be talking about how to build a full adder, how to build a 4-bit calculator using individual transistors, how to turn this 4-bit calculator into a 4-bit computer, and then from there we'll be talking about more advanced computational methods such as analog computing, neural networks, and we'll be working our way towards creating non-biological human consciousness. At the Global Science Network, we focus on 3 main projects. First, solving the world's energy problems with a novel renewable energy technology. Second, solving unified field theory. And third, creating non-biological human consciousness. If this sounds like something that you would be interested in working on, check out our website, gsnetwork.com, subscribe to our email list there, and subscribe to our YouTube channel. Here are all the logic gates and the names of all the logic gates. This way, if you have a question, you can refer to the logic gate by name. For reference, here are the names and symbols of each type of logic gate. And what you'll notice is this column is basically the inverted logic of this column. For example, an AND gate, the output is off, 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 on. And for a NAND gate, the output is on, off. All of these digital logic gates are based on using an individual transistor as a switch. This NPN transistor has 3 pins, which are the emitter, the base, and the collector. This NPN transistor has a model number of 2N2222, which is very similar to model number 2N3904, and either of these model numbers will work for all of the circuits we're building in this video. Here is the symbol for a transistor. We can see it has the emitter, the base, and the collector. The emitter goes to ground. The base has a positive supply voltage, and the collector has a positive supply voltage. And how a transistor works is when you have current flowing from the base to the emitter, that allows current to flow from the collector to the emitter. Again, here is a symbol for a transistor, but a better way to draw this symbol would actually be using 2 diodes. And what we know about diodes is current can only flow in one direction. So current can flow from here to here, or from here to here. Since our ground is on this side, current wants to flow from the base to the emitter. And a simplified version of the semiconductor physics is when current is flowing from the base to the emitter, this diode basically goes away and current can flow from the collector to the emitter. Here we have a simple example of how a transistor works as a switch. And what happens is whenever I touch the base of this transistor with my finger, this LED will turn on. However, this is kind of a trick because if I remove my finger from the right side and then I touch the base of this transistor, it does not work. So what's actually happening is current is flowing from the positive 5 volts through my body and then into the base of this transistor. A simpler way to see this would be if I touch the collector to the base, you can see that current is allowed to flow. So what's actually happening is current is being taken from this positive 5 volt side and then being applied to the base, which allows current to flow from the base to the emitter, which allows current to flow from the collector to the emitter. So essentially what I'm doing is using my finger to complete the circuit. This circuit shows how a transistor works as a switch. Whenever the input is off, the output should be off. Whenever the input is on, the output should be on. Right here you can see the transistor, and we have the emitter of the transistor hooked up to ground by going through this black wire. We have the base of the transistor hooked up to the positive 5 volt rail by going through this red wire, across the switch, and then across this 2K resistor. And finally we have the collector of the transistor also hooked up to the positive 5 volt rail by going through this 2K resistor and then across the LED. Let's see if the circuit works. Whenever we press the button, the LED turns on. Whenever we release the button, the LED turns off. So how exactly is the circuit working? Whenever we press the button, this allows current to flow from this positive 5 volt rail into the base of the transistor, out the emitter, which goes to ground. And when this happens, current is then allowed to flow from this positive 5 volt rail across the 2K resistor, across the LED, through the transistor, and then also out to ground through this black wire. Now we're going to talk about the inverter. Whenever the input is off, the output is on. Whenever the input is on, the output is off. This circuit is set up very similar to the switch, where the emitter of the transistor is hooked up to ground through this black wire. The base of the transistor is hooked up to the positive 5 volts by going through the red wire, across the switch, and then across the 2K resistor. The difference is the collector is actually hooked up directly to positive 5 volts by just going through a 2K resistor. And the LED is actually set up differently, where it's actually turned on right now because current is flowing from this positive 5 volt rail across the 2K resistor, through the LED, and then into ground by going through the black wire. Whenever we press this button, the LED turns off. It turns off because current is now flowing from this positive 5 volt rail into the base of the transistor and out to ground. And whenever this happens, all of the current from this positive 5 volt rail goes to this first ground rather than the second ground. And why exactly does that happen? It happens because whenever current is flowing from the base to the emitter, up to 100 times the current is actually allowed to flow from the collector to the emitter. So whenever this happens, this transistor actually turns into basically a very small resistor as far as current flowing from the collector to the emitter is concerned. So if you have a very large resistor and a very small resistor, most of the voltage drop is going to happen across this resistor. And you're actually going to have a voltage drop of 4.984 volts across this 2K resistor. And this only leaves 0.016 volts to try and go across this LED. This is a yellow LED, which actually requires 1.9 volts for any current to flow across it. So none of the current is going to flow across this LED to ground, and all of the current is going to flow from this positive 5 volt rail across the 2K resistor, across the transistor, and then out to this first ground. And that's actually important because in the circuits coming up, we're not going to have an LED here, but we're actually going to have a second transistor. And for a transistor, the needed voltage drop is going to be 0.7 volts, which is still going to make it so that no current flows to this alternate ground. So just pay attention whenever we're doing our next circuits, and you're going to see a very similar pattern where we have a resistor hooked up to the positive 5 volt rail going to a second ground. Sometimes current will be flowing to that second ground, and sometimes current will not be flowing to that second ground. This circuit is not any particular logic gate. We actually have a switch and an inverter, and both of these are hooked up to positive 5 volts by going through the switch and then going into the inputs of the transistor, which is the base of the transistors. And you can actually see that this is opposite logic. So if we press the button, they actually do the opposite thing. And you can actually see how these are wired up differently, where the inverter has a second ground and the switch does not. The main reason I wanted to show you this circuit is to explain how the output is sent. So from this inverter, you can see that the output gets sent to the second ground, and it can actually be sent to a third ground. Whenever we toggle the switch, the inverter still works as expected. Now let's look at what happens if we try and send an output to a different point in the circuit from this switch. This would be one possible location to try and send that output from, and you can see that it does not work. The switch works as expected, but this output just stays on all the time. Next, let's see what happens if we try and take the output from right here. Whenever we toggle the switch, this second output is actually doing the same thing as the inverter. So that is not what we want out of a switch. Now let's see what happens if we try and take the output from the emitter side. It does not work as expected. However, we can modify this circuit to work in a useful way. To modify this circuit, we're actually going to take this 2K resistor, and rather than having it go from the positive 5 volt rail, we're actually going to connect it to ground, and we're actually going to just use this red jumper to go directly into the collector of the transistor. And rather than have this black jumper right here, we're actually going to go to this ground using a 2K resistor. Here is the new layout, and we have the collector of this transistor connected directly to positive 5 volts. The emitter of the transistor is connected to ground by going across this 2K resistor. The reason that this is beneficial is because now the positive 5 volts can make its way across this red wire, across the transistor, and whenever it gets to here, it still has enough voltage that it can be sent as a usable output. So now the output can be sent to this ground, and this LED will light up. Let's test the circuit to see if it works. And it does. Whenever we press the button, the LED turns on. Whenever we release the button, the LED turns off. So this switch is working properly. But this switch, since it can actually send an output, is actually a buffer rather than a switch. And in this configuration, it's actually very similar to an emitter follower. Since all we're trying to do is send an output across an LED and going to this ground, and we know we're going to have another resistor here, I found that this circuit actually works better if we remove this resistor right here. So if we remove this resistor right here and we test the circuit, we can see that it does work properly. And now let's take a closer look at this circuit. Here is the circuit that we were just looking at. We're going to call it buffer 1. And if you just look at the truth table, it might not seem super useful because whenever the input is off, the output is off, and whenever the input is on, the output is on. However, this circuit is actually useful because we can actually feed in a very low current value into this transistor, a value that would be so low that it would never light an LED, and we can turn it into a value that will light this LED. Let's look at how this works. So right here we have a 1000K resistor, which is also called a 1 meg resistor, and that is going to be fed across this switch and into the base of this transistor. This is actually only going to provide 0.005 milliamps of current. However, that current is actually going to be multiplied by about 100 whenever the current comes from this positive 5 volt rail. So we're going to have current come from this positive 5 volts, go across this transistor, across the LED, and then into this ground right here. So let's see if it works. Whenever we hit the button, the switch does work as expected. Alright, here we have buffer number 2. Right here is the buffer, and this is kind of how I intuitively thought a buffer should work. We have an input resistor right here of 100K. So this is a 100K resistor, and right now it's just coming from this positive 5 volts, going across the LED, and then going to ground. And you can actually see that this LED is barely lit up. It is lit up, but it's just very slight. The voltage drop across this LED is around 1.9 volts, but there's just almost no current going across this LED, which is why it's so dim. Now if we actually plug in our buffer, we can actually see that rather than having this really poorly lit LED, we have an LED that is really bright. And that is the point of the buffer. Now let's look at how this circuit is working. We have positive 5 volts coming right here. It goes across this red wire and into the base of this transistor. So now all of the power from this resistor right here is going to go across this transistor and into this ground. And none of the power is going to go across this blue jumper and into the base of this transistor. That means none of the current from this resistor right here is going to go to this ground, and all of the current is going to go across this LED and into this ground, which is why this LED is lit up. Now we're going to remove this input by taking out this resistor. Now we do not have any current going into the base of this transistor right here. That means all of the current from this resistor right here is going to go across this blue jumper and into the base of this transistor. This means that all of the current from this resistor right here is going to go across this transistor and into this ground, and none of the current is going to go from this resistor to this ground, which is why the LED is turned off. Now there actually is a limit to this buffer working, so we actually swapped this 100K resistor with a 1000K resistor or a 1 meg resistor, and now the current from this resistor does feed into the base of this transistor, which allows current to flow from this positive 5 volt rail to this ground. However, the voltage drop across this resistor is 4.28 volts. And this means that you still have 0.72 volts here that can go across this blue jumper and into the base of this transistor. The voltage required to turn this transistor on is actually only 0.7 volts. So we actually will have current flow from this resistor to this ground over here, and none of the current is going to flow from this resistor to this ground here. So this LED is actually off even though our input is technically on. And that's because our input current was too low. This is buffer number 1 and this is buffer number 2. Buffer number 1 actually did a better job at taking a low current source input and turning it into a high current source output. However, buffer number 1 actually sends the output from the emitter side of this transistor. And this is actually the only circuit that we're going to be looking at today that sends the output from the emitter side of the transistor. All the other circuits are going to be more like buffer number 2, where the output is sent from the collector side of the transistor. Resistor values for LEDs is something I wanted to talk about, so let's take a look at this. Right here we have a 330 ohm resistor. This is a 1K, 2K, 10K, and 100K. So whenever we connect power here, we can actually see the difference in brightness based on the resistance value. The supply voltage is 5 volts, and these LEDs are actually rated to 20 milliamps. This means the lowest resistor value that we would want to use is 250 ohms. So this 330 ohm resistor is safe, and you can see that the LED is super bright. It's actually so bright that it's kind of obnoxious in the camera, which is why I try and stay away from low resistor values. I typically try and use resistor values around 2K because you can tell that the LED is on, but it's not super bright. If you go to this 100K resistor, this LED is on, but it's just so dim you can barely see it. For all of the digital logic gates in this video, you can actually use resistor values anywhere from 330 ohm to 2.2K, and everything should work as expected. If you want the LED to be a little bit brighter, you can use a lower resistor value, and if you want the circuit to be a little more power efficient, you can use a larger resistor value. Now this is getting exciting. AND gate 1. So for an AND gate, if input A and input B are on, then the output will be on. But in all other cases, the output will be off. So let's test the circuit to see if it works. If we press input A, the output will be off. If we press input B, the output will still be off. But if we press input A and B at the same time, the output will be on. So how exactly is this circuit working? So we have the inputs coming from this positive 5 volt rail going across the switch through the red wires and into the base of each transistor. If we have current flowing from this input A into the base of this transistor, it would allow current to flow from the collector to the emitter and out this ground. But this only happens if we have a positive 5 volts on this side of the transistor. And that's only the case if this transistor is turned on as well. So if this transistor is on and this transistor is on, current will flow from this positive 5 volt rail across the LED, across both transistors, and then into ground through this black wire. This circuit is AND gate 1 and this circuit is AND gate 2. These are actually built the same way, except for AND gate 1 has a whole bunch of extra components. So AND gate 1 has these switches and these red wires, and rather than use the switches and red wires, we can actually just connect the base of each transistor directly to the positive 5 volt rail by going across the resistor and then just going directly into the base of each transistor. And rather than have this green wire, we can actually just connect the collector of transistor 1 in the same line as the emitter of transistor 2, and this allows these to be electrically connected without having the green wire. This first AND gate made it a little bit more clear how this was working and allowed us to use the switches, but in most cases, whenever you're building these logic gates, you want it to be as compact as possible, and that's what AND gate 2 allowed us to do. This is AND gate 2. You can see the circuit is a lot more compact and the circuit diagram is a lot more compact. Now input A and input B are just connected through these resistors. However, to test the circuit to see if it's working, we actually have to pull out these resistors. So we're going to pull out input A and the circuit will turn off. Whenever we put input A back in, so inputs A and B are both on, the output of this circuit will be turned on. And this is actually how most people show how to build an AND gate. However, this will only work as a standalone circuit or as the last circuit in the series. If you actually look at the output, it's actually being turned on by going from this positive 5 volt rail across the LED through the transistors and then into this ground. It's not going from this positive 5 volt rail into a ground over here. So this output cannot be sent further down the circuit. This was AND gate number 2, and this is AND gate number 3. AND gate number 3 uses 3 transistors rather than 2, which is a bit more complicated, but it is also more useful. If we look what's going on right now, we have input A and input B turned on, which turns the output to on. And how this circuit is working is right now, all of the current from this third resistor here is flowing through the transistors and into this ground, which means none of the current is flowing from this positive 5 volt rail into the input of this third transistor. And since this third transistor is basically off, all of the current from this positive 5 volt rail is flowing across the LED and into this ground, which is why the LED is turned on. Now, if we remove one of these resistors, it turns the circuit off. So what's actually happening now is all of the current from this positive 5 volt rail is going into the input of this third transistor and into this ground, which allows current to flow from this positive 5 volt rail into this ground through this transistor, and none of the voltage is flowing from this positive 5 volt rail across the LED and into this ground. The output from AND gate 3 is going from this positive 5 volt rail to this ground, which means it can be sent to other points further down the circuit. AND gate 4 is actually built using 2 NAND gates. Since we haven't talked about how to build NAND gates yet, we'll come back to this circuit towards the end of the video. AND gate 5 is actually built using 3 NOR gates. And since we haven't talked about NOR gates, again, we'll come back to this circuit towards the end of the video. If you're only going to understand how to build one logic gate, this is the one to understand. It is a NAND gate. This is a universal logic gate that can be used to build every other type of logic gate. Whenever inputs A and B are both on, the output is off, but in all other cases, the output is turned on. If we look at our circuit, right now we have inputs A and B both on, which is why the output is off. So right now, all of the current from this third resistor is flowing across these transistors and into this ground, and none of the current is flowing from this positive 5 volt rail across the LED and into this ground. Now, if we remove input A, the LED turns on. It turns on because now none of the current from this positive 5 volt rail is going through the transistors and into this ground, and all of the current is flowing across the LED and into this ground. Now let's look at an OR gate. For an OR gate, if inputs A and B are both off, the output will be off, but in all other cases, the output will be on. If we look at our circuit, right now we have inputs A and B turned on, which has the LED in an on state. If we were to remove input A, the LED should stay on, and if we remove input B, so now we have A and B off, the LED turned off, which is what we expect. We reconnected power into input A, which is why the LED is turned on. Now let's look at how this circuit is actually laid out. You'll notice that there's this orange jumper, which actually connects the collectors of both transistors together. What this allows for is whenever there is current flowing from this positive 5 volt rail, it goes through this LED and then into the collector of both of these transistors. This makes it so that only one of these transistors needs to be turned on to allow current to flow from this positive 5 volt rail to one of these grounds. For example, when input A is turned on, current is allowed to flow from the base to the emitter of transistor 1. This then allows current to flow from this positive 5 volt rail through the LED into this orange wire, through the transistor, and then out to ground through this black wire. When input B is turned on, current will flow from this positive 5 volt rail across the LED, across the transistor, and into this ground. When input A is turned off, the current from this positive 5 volt rail cannot go across either of these transistors, which is why this LED is turned off. When both A and B are connected, current can flow from this positive 5 volt rail through the LED, through either or both transistor, and into either or both ground. So this LED is definitely going to be on. This is OR gate number 1, and this is OR gate number 2. You can see OR gate number 1 only required 2 transistors, and OR gate number 2 requires 3 transistors. That's because this OR gate can actually send information to other logic gates. This OR gate can only work as a standalone OR gate or as the last OR gate in this series. So in most cases, you're actually going to want to build OR gate number 2. This is OR gate number 2, and you can see right now that we have inputs A and B turned on. So if we want to check the circuit to see if it's working, if we remove input A, it should stay on. And if we remove inputs A and B, it should shut off. So that is working as expected. I reconnected input A, which turns this circuit on. So let's look at how this circuit is actually working. With input A being turned on, we have power going from the base of this first transistor and into this ground. When this is happening, all of the current from this positive 5-volt rail is now flowing into the orange jumper and then into the collector of this first transistor, through the transistor, and then into this ground. That means that none of the current from this positive 5-volt rail is flowing into the input of this third transistor. And since no current is going into the input of this transistor, that means all of the current from this positive 5-volt rail is flowing across the LED and into this ground, which is why it is turned on. Now, if we remove input A and we look at what's going on, now none of the current is flowing from this positive 5-volt rail into these grounds, and all of the current is going to go across this blue wire and into the input of this third transistor. This is going to make all of the current from this positive 5-volt rail flow into this ground rather than this ground, which is going to turn the LED off. This is OR gate number 3, which is actually built by using 3 NAND gates. We can actually see that input A is right here and input B is right here. Notice that it's not the first 2 resistors, but it's actually the first and the third. And in the circuit diagram, we can see that input A is here and input B is here. Right now, with input A and B both being on, the output is on. If we were to remove input A, the output is still on. If we remove input A and input B, the LED will turn off. I have reconnected inputs A and B, and we can see that the LED is turned on. So let's look at how this circuit is actually designed. This NAND gate actually has both inputs of the NAND gate connected via this red jumper, and so does this NAND gate. And if we look at how it's supposed to be built, that is how it is supposed to be built. So with this input being turned on, this NAND gate is actually turned off. It's turned off because all of the current from this positive 5-volt rail is going to flow across these transistors and into this ground rather than go into the output. And the same is true with this NAND gate. So if we actually have both of these NAND gates being off, or if even one of these NAND gates is off, all of the current from this positive 5-volt rail is going to flow across this LED and into this ground rather than across both of these transistors and into this ground. And that's actually how this circuit works. So now if we actually have inputs A and B turned off, now the output of both of these NAND gates is on. So this one is on and this one is on. So now the current from this positive 5-volt rail flows across these 2 transistors and into this ground rather than this ground, which is why the LED is off. OR gate number 4 is built using 2 NOR gates. We actually haven't talked about how to build a NOR gate yet, but I think you'll be able to follow this circuit. Right now we have inputs A and B turned on, which is why the LED is turned on. And if we remove input A, the LED should still be on. And if we remove inputs A and B, the LED should shut off. I have now reconnected power into inputs A and B, which is why this LED is turned on. Let's look at how this circuit is actually built. Again, it is built with 2 NOR gates, and the logic for a NOR gate is if inputs A and B are turned off, then the output will be turned on. But in all other cases, the output will be turned off. So right now, we have the inputs of A and B going into the inputs of this first NOR gate. So if both of these inputs are on, the output is going to be off. So right now, the output from this positive 5-volt rail is actually going to be flowing into these grounds rather than flowing into the inputs of this second NOR gate. So if the inputs of this NOR gate are off and off, the output of this NOR gate is going to be on. So this positive 5 volts from here, all of the current is going to go across the LED and into this ground, rather than from this positive 5 volt rail into these two grounds. Now if we remove input A and input B, the LED is going to shut off. So it shuts off because right now all of the current from this positive 5 volt rail is not flowing into these grounds, but rather flowing into the inputs of this second NOR gate. If both of the inputs of this second NOR gate are on, then the output is off. So all of the current from this positive 5 volt rail is flowing into one of these two grounds rather than flowing across the LED and into this ground. This is another universal gate called a NOR gate. And with a NOR gate, if inputs A and B are both off, the output will be on, but in all other cases, the output will be off. So right now, we have inputs A and B on, so the output is off. And if we remove input A, it should stay off, and if we remove A and B, it should turn on. I reconnected input A, so the circuit is off, and let's go through real quick how this circuit works. So right now, with input A being on, current is flowing from the base to the emitter, which is allowing current to flow from this positive 5 volts across the orange jumper, across that transistor, and into this ground, rather than going from this positive 5 volts across the LED and then into this ground. Now, if we remove both inputs A and B, the light is turned on because now the current from this positive 5 volt source cannot flow to either of these two grounds, so it has to flow across the LED and into this ground. This is an exclusive OR gate, and it's just like a regular OR gate, except for whenever inputs A and B are both on, the output is off. So if we look at our circuit right here, right now we have inputs A and B on, and we can see that the output is off. Now if we remove input A, it should turn on, and then if we remove input A and B, it should shut off, which it does. This exclusive OR gate might seem complicated at first, but it's actually not that bad if you break it down. What we basically have is these two transistors acting like a NAND gate, and these two transistors acting like an OR gate, with this transistor acting like a switch in one situation. So right now we actually have inputs A and B both on, which actually makes it so the positive 5 volts from this resistor will go across both of these transistors and into this ground, which means the output of this positive 5 volts will not go into this transistor, which is acting like a switch. And since this switch is basically off, because no current is flowing from the base to the emitter, that means that no current can flow from this positive 5 volt rail into this ground. So the LED is going to be turned off, which is actually what we want, because we can see whenever A and B are on, the output is supposed to be off. Now we will take out one of the inputs and we will look at what happens. So whenever we remove input A, the LED turns on. The LED turns on because all of the current from this positive 5 volt rail can no longer flow across these two transistors into this ground. Rather, all of the current will flow into the input of this transistor. Since we have current flowing into the input of this transistor and going to ground, now this switch is turned on if we have current flowing from this positive 5 volt rail to this transistor. And if either of these OR gates is turned on, we will have current flowing into this transistor. So from this positive input of input B, it's going to flow into this yellow jumper, across and into this transistor right here. And since this transistor is turned on, we can have current flow from this positive 5 volt rail across the LED, across this transistor, across this green jumper, and then this switch is on, so current can pass through the transistor and into that ground. Now the final case would be if we remove input A and B, we can see that the LED is turned off. It is turned off because the positive 5 volts from this side can no longer reach either of these grounds. It can't reach either of the grounds because this transistor is off and this transistor is off. There actually is current flowing into the base of this transistor, but it doesn't matter because any current that's trying to reach these grounds is stopped from this transistor or this transistor. This is exclusive OR gate 1 and this is exclusive OR gate 2. These circuits are identical except for exclusive OR gate 2 uses one additional transistor that allows us to send the output to other logic gates. So this exclusive OR gate can be used as a standalone exclusive OR gate or as the last exclusive OR gate in a series of logic gates. However, this exclusive OR gate can be used in all cases. This is exclusive OR gate 2, and it's so similar to exclusive OR gate 1, I'm not going to go through exactly how it works. The only thing that's different is now we added this additional transistor, and this changes how the output is being sent. So now the output is going from this positive 5-volt rail here across the LED into this ground whenever the circuit is turned on. Whenever the circuit is turned off, it will be going from this positive 5-volt rail across this transistor and into this ground. Here we have exclusive OR gate 3, which is actually built by using 4 individual NAND gates. And you can actually see how those NAND gates are supposed to be wired up right here. Let's see if this circuit works. Right now we have input A and input B turned on, which means the output is off. If we remove input A, the circuit should turn on. And if we remove input A and input B, the circuit should turn off, which it does. Now, I'm not going to go through exactly how these gates turn on and off to get this logic for the exclusive OR gate 3, just because it would be a little bit long-winded. But for comparison, let's compare exclusive OR gate 2 with exclusive OR gate 3. Exclusive OR gate 2 only required 6 transistors and can be used in any situation. Exclusive OR gate 3 actually isn't bad by using these 4 NAND gates. It requires 8 transistors and it can also be used in any situation. Either one of these will work if you need to build an exclusive OR gate. However, exclusive OR gate number 2 does have the upper hand because it requires 2 less transistors. Here we have exclusive OR gate number 4, and this is actually built using 5 NOR gates. So right here you can see how those NOR gates are supposed to be connected. Here is our circuit, and let's see if it works. Right here we have input A, and right here we have input B. And right now they're both on, and the output is off, which is what we expect. And if we remove input A, it turns on, and if we remove input A and input B, it turns off. This circuit is built using 5 NOR gates, which means it's going to take 10 individual transistors to build this circuit. And you can see it actually takes up the whole top half of this little breadboard, so I actually had to make the last connection down here. And I'm not actually going to go through the logic of this one either because it would be rather long-winded. This is one of those circuits where if you need an exclusive OR gate, this is not going to be your best option. This is one of those cases where I built it to show you that it works, but hopefully you won't have to build it. Here we have an exclusive NOR gate. And for this, if only input A or only input B are on, then the output will be off. But for the other cases, the output will be on. So let's look at what we have here. Right now we have input A and input B turned on, so the output is on. Now if we remove input A, the LED will turn off, and if we remove A and B, the LED should turn on, which it does. This would be the other case with only input A, and we can see that the circuit is also off. Let's go through the logic of how this circuit is working. Right now we have inputs A and B turned on, which means all of the current from this positive 5-volt source is going to go to this ground, and this transistor is going to be turned off. If this transistor is off, that means none of the current from this positive 5-volt source can get to this ground, which means all of the current from this positive 5-volt source is going to go across this LED and into this ground. Now, if we remove input A, we can see that the LED turns off. So now all of the current from this positive 5-volt source does not go to this ground, but rather it turns this switch on. So now current can flow across this transistor. And now since input B is on, this input B will go into this yellow jumper and into the input of this transistor in this OR gate. So now we have current flowing from this positive 5-volt rail into this transistor, across this green jumper, which puts it into this transistor, which means current will flow from this positive 5 volt rail all the way to this ground. And none of the current will flow from this positive 5 volt rail into this ground, which is why the LED is off. And finally, we have the case where inputs A and inputs B are both off. And in this case, all of the current from this positive 5 volt rail can't get to this ground because both of these transistors are turned off. And since they're both off, all of the current will flow from this positive 5 volt rail across the LED and into this ground, which is why the LED is on. As promised, we are coming back to AND gate 4, which is built by using 2 NAND gates. And now that you understand how NAND gates are built, you should better understand this circuit. Right now we have input A and input B turned on, which is why the circuit is turned on. And if we remove either of these or both of these, the circuit should turn off, which it does. Now let's look at how this circuit is supposed to be built. The output from NAND gate 1 is supposed to feed into input A and B of NAND gate 2. And if you look at how we have this wired up, that is how it's wired up, where we have the output of NAND gate 1 feeding into the inputs of A and B. Now we can look at how this circuit works. Right now, with A and B being on, all of the current from this positive 5 volt source is going to flow across these transistors and into this ground, which means the output from this positive 5 volt rail is going to be off for both of these. And since the output is off for both of these, all of the current from this positive 5 volt rail is not going to flow into this ground, but rather it's going to flow across the LED and into this ground, which is why the LED is turned on. Now, if we remove one or both of these inputs, the LED turns off. So now we can see that all of the current from this positive 5 volt rail is not going to be able to flow across these transistors and into this ground, which is going to make the input of both of these transistors on. And now that both of these are on, all of the current from this positive 5 volt rail is going to flow into this ground rather than this ground, which is going to turn the LED off. And this is going to happen if input A is turned off, if input B is turned off, or if input A and B are turned off. This is AND gate 3, and this is AND gate 4. AND gate 4 was built using 2 NAND gates, and it required 4 transistors. This is not a bad way to build an AND gate, and it will work in any situation, but this is actually still the better way to build an AND gate in most situations, because it only requires 3 transistors and it will work in any situation. The only case that I can think of where you would want to use NAND gates to build an AND gate would be if you had an integrated circuit that had, say, 4 NAND gates built into it. You could then use 2 NAND gates to build an AND gate, and you wouldn't have to have a separate integrated circuit for each type of gate. Here we have AND gate 5, and it's actually built by using 3 NOR gates. Right now, we have input A and we have input B both on, which is why the output is turned on. And if we remove input B, it should shut off. I'm removing input B because it's a little bit less clear where it is. And it does shut off, and if I remove input B and input A, it should stay shut off, which it does. This circuit is built by using 3 NOR gates, which means we need 6 individual transistors to build one AND gate. And this is not ideal because AND gate 3 only required 3 transistors and worked in all cases. However, this circuit does work if you need to build an AND gate and you want to build it using NOR gates. Now I'm going to show you how to implement AND gates using integrated circuits. This is AND gate 6 and this is AND gate 7. And both of these are built using these integrated circuit chips. The serial number of the chip is SN74LS08. And each one of these chips actually has 4 AND gates built into the chip. We're going to be using AND gate 1, which has the inputs of 1A and 1B and an output of 1Y. First, we will look at AND gate 6. Here we have AND gate 6, and let's look at how it's wired up. You can see pin 14 is supposed to go to VCC, so we have our positive 5 volts going into pin 14. Pin 7 is ground. We have pin 7 going to ground. Pin 3 is actually our output. So we actually have pin 3 going through this blue wire across the 1K resistor and then into this LED. which is what we want. And we actually have the inputs wired up a little bit strange. Input A and input B are actually wired by going through this black wire, across the switch, and then into these grounds. Right now, both of them are on, so we actually have both of these wired to ground right now, which is why the circuit is off. However, if we actually switch both of these to be on, you can see that this LED turns on. And what we're actually doing is not putting a ground or a positive input into A and B. So if these are actually just floating, they actually by default turn on. So now by default both of these are on, so the output of our AND gate is on. The reason that these are actually on by default is there's actually a pull-up resistor within this integrated circuit that makes it so if you have no input into the input, it's actually on rather than off, which might seem a little strange, and you'll actually see a lot of people wire up their integrated circuits this way. I don't particularly like it because sometimes this TTL logic works and it's stable, and sometimes it does not. So you'll actually see this LED flickering a lot, so this is not how I recommend wiring up these integrated circuits. By adding resistors going from this positive 5-volt rail into input A and input B, we make wiring up this circuit this way a lot more valid. So now we can see that with this switch being off, these inputs are both set high because positive 5 volts is actually coming from this positive 5-volt rail and into the inputs. And whenever we actually turn the switches on, now the positive 5 volts from these resistors is actually flowing across these black wires and into ground here, which is why this LED is turned off. This is still a valid way to wire up this integrated circuit, but I'm actually going to show you how to wire it up better with AND gate 7. This is AND gate 7, and you can see it is wired up very similar to AND gate 6, where we have VCC going to pin 14, we got our positive 5 volts going to pin 14, we have pin 7 going to ground, we still have pin 3 going through this blue wire across the 1K resistor and then into the LED. The difference is how we're doing the inputs. So right now we actually have the inputs coming from this positive 5-volt rail through the switch, through these red wires, and into input A and input B. So this is actually how you would think of the circuit working, where we actually have a positive input into A and a positive input into B, which is why we have the output being turned on. Now whenever we turn off one or both of these, the circuit turns off, which is what we expect. Now you'll notice that we actually had to add these two resistors here into ground, because if we didn't add these resistors, whenever this switch was turned off, these would be floating and they would actually be still interpreted as an on to the integrated circuit because of that pull-up resistor. So if you add these two resistors to ground and you have your inputs coming from the positive 5 volts, this circuit works exactly how you would expect. And this is the way I would recommend wiring up these integrated circuits. Now you might be asking yourself, which of the 5 AND gates that I showed you how to build are actually built within this integrated circuit? And the answer is none of them. If we actually look at the data sheet, we can actually see that one AND gate is built this way or this way. This particular AND gate actually requires 1, 2, 3, 4, 5, 6 transistors. This is the one that's actually built on the chip because it's the LS08, and this one is actually built with Schottky transistors and Schottky diodes. So this one is actually built for low power consumption, fast switching times, and has an overall robustness of the circuit, so it will work in a lot of cases. However, with that robustness might come some features that you actually don't like. So sometimes it's actually just easier to build AND gate number 3, and sometimes it's easier to use these integrated circuits. And we can actually see how these circuits are built within the integrated circuit, because this particular integrated circuit actually has a viewing window. And you can actually see at the very center there's a silicon wafer. And on that silicon wafer, all of these different components are placed through a series of microfabrication processes. And then you can see that there's a whole bunch of wire bonds going to that silicon wafer that connect to all of the pins on the outside of the integrated circuit.